Hello, Chemistry of Earth and Space Science. We are still in Unit 3, Dangerous Compounds, but now we're on the second half of Lesson number 2, where we deal with electron configurations. So our goal here is to be able to understand the arrangement of electrons in an atom or an ion, and we're also able to draw an orbital diagram, to write an electron configuration, and to write the abbreviated electron configuration, or the shorthand. So what is an electron configuration? Well, what it is, I'll say a code that has us able to describe where the electrons are in an atom, all of them, as regards to 2 or 3 different aspects. One of them is what energy level the electron's on with the Bohr model, and then also the orbitals, because as we'll find out, the electrons and those orbitals, according to Bohr, are not ideal. They actually have a lot more beneath the surface. So taking a step back, we had the Bohr model. This is one we saw when we did the initial piece with the sun and the fusion and fission and the nucleus. So obviously a typical atom, according to Niels Bohr, was a nucleus that had the protons and neutrons, and then the electrons buzzed around, and Niels Bohr was the one who said they're on energy levels, not necessarily just flying around willy-nilly. So one of the benefits of the Bohr model was the fact that it had its energy levels, so we're going to adopt that as our first level. So a way to look at electron configuration is we're going to use 4 different values to describe where an electron is. And the first value is simply what is the principal quantum number, or fancy word for energy level. What is the energy level according to the Bohr model? So if we go back to our shells, the first shell is 1, the second shell is 2, third shell is 3, so on and so forth, until you get to, in our case, the 7th shell on the electron. So now we have a shell according to the Bohr model. Now we're going to look a little closer. Now, realistically, what was found after Bohr had devised his concept of the atom was he noticed that, or we noticed as a scientific community, that those levels had sublevels. And what I mean by that is every single one of the shells, according to Bohr, had sublevels to them, but the sublevels just represented the different shapes that those shells were in. Now, I don't want to make this too weird, but I know we represent the atom much like the Bohr model with that sphere around a centrally located nucleus. However, we have found that those electrons do not all occupy a spherical pathway. They sometimes will take some really weird pathways. I'll show you some pictures in a little bit. But those pathways that they take are going to have different shapes. They're not all going to have the same spherical shape that we think of when we think of Bohr model. They're going to have different shapes. So we want to ask ourselves first, how many sublevels does each energy level have? Well, the really cool part is the first energy shell only has 1 sublevel. So it only has the 1 level. There's not 2 levels that come from, 2 or more levels that come from the first shell. The second shell, well, that one has 2 sublevels. The third shell has 3. You can see where we're going with this mathematical modeling, this mathematical premise, and still keeping with the truth of amongst what we see. The 4th level is going to have 4, and so on and so forth. Now, instead of identifying the sublevels with another number, like to say the first sublevel of the second energy level, we give these sublevels names. And actually the letters are significant to what the shapes are. So we use the letters S, P, D, and F, and you'll see that we'll go past that after F in a theoretical way. S, P, D, and F represent the shape. There's an S-shaped orbital, there's a P-shaped orbital, there's a D-shaped orbital, and there's an F-shaped orbital. And they take different paths than the traditional, sorry, the traditional spherical paths. So that one has one sublevel, that's going to be the S. The second one has two, that's going to be an S and a P. The third one's going to have three, that's going to be S, P, and a D. The fourth one has four, that's S, P, D, and F. And if we go past that, we're still going to have more orbitals with more letter designations, but past there, they're theoretical. And what I mean by theoretical is no atom has had electrons in their ground state in any sublevel greater than F. Now, if we think in terms of this is a mathematical model to explain where the electrons are, and so far for 118 atoms, we've been spot on, we're about ready to embark upon a time when we may start seeing some changes, and this is when we get a chance to see whether G is the next sublevel. G will come with element number 121. Element 121, when it's discovered, or if it's discovered, should have a G sublevel. So it's kind of like one of those things of be on the lookout. 6 could have 6 sublevels, but S, P, D, and F are the only ones that are occupied at this point. We also have theoretically a G and H. And 7 has a G, H, and an I. So what does this look like, this arrangement of the orbitals? Well, if it took a visual, you say there's the 1s, there's the 2s and the 2p, there's a 3s, 3p, and 3d, 4s, 4p, 5d, 4s, 4p, 4d, 4f. And then past there, we start having the theoreticals. 5s, 5p, 5d, 5f. We've seen electrons in all those subshells, but there would be 5g, which, again, we have not seen an electron in that sublevel because the atoms just haven't gotten that large yet. Same thing here. 6s, 6p, 6d, 6f puts it on a theoretical because you're going to see as the energy levels go, we do not have an atom that has an electron in the 6f orbital. And continue the 7th, which is 7s, 7p, 7d, dot, dot, dot. The ones that are in orange are the ones that have there's no atom in the ground state that has electrons in that particular sublevel. And I don't know whether you get a feel for this, but the idea is that these things are going to not fill in a very conventional way. So we're going to talk about that in a second. So if we have energy levels and they have subshells, and those are called the orbitals, within the orbitals, each one of those sublevels or those orbitals have different orientations in space. And I'm going to show you some pictures in a second to kind of make sense of this, and it's pretty wild. So when looking at the S orbital, that one orientation, S can only be one way, because actually S is shaped like a sphere. Okay, so it could be only one way. Let me show you this. I'm going to make a quick change here. This is what the S orbital looks like. So the S orbital looks like a sphere. I can't point this in more than one direction and have it have some significance. So S has just the one subshell. If I go back to P, there are 3 orientations for the P. Okay, so 1, the S has 1, the P has 3. Let me show you the P's. This is the P orbitals. Notice with this shape, the P stands for poles. With this shape, I could point those in either along the x-axis, the y-axis, or the z-axis. And those are 3 different directions, perpendicular to one another that these electrons could occupy. Now, when we say occupy, it means they're on the surface of these what look like balloons. Okay, so the p orbitals are this. The shape is the dumbbell, or the polar, with it looks like two balloons attached to one another, but they can be pointed in three different orientations: along the x, along the y, and along the z. Next comes the d. The d has 5 orientations. Okay, 5 orientations. So see this trend. S has 1, P has 3, D has 5. Okay, and what do you think F would have? What's the next number that would be in this pattern? It would be 7. So there's 7 orientations for the F. Now, if we had A, G, H, I, they would have the prescribed number of electrons, so orbitals. So G would have 9, H would have 11, I would have 13. So I already showed you the S and the P. I'm going to show you the D and the F. Now, this is where things got kind of off the rails because the shapes of the D orbitals are not all 4 identical. There are 4 that look identical to one another, and then there's the weirdo. So we have 4 different orientations that have this double dumbbell shape. That's why it's called D. It's dumbbell shape. It's got 2 dumbbells, 4 balloons on a plane pointing at 90-degree angles from one another, and they can either occupy the XY plane, the XZ plane, the YZ plane, and in the case of these last 2 down here, this one here and this one here, they're actually on diagonals of the planes. So we have these 5 orientations. And then the 5th one, this wackadoodle, where it looks like a snowman with a hula hoop. I don't know. This is the 5th shape. So this is where things get a little less clean because you say that they all have the same shape, sorta. The d orbitals, one of the shapes is odd. The same thing's true with the Fs. Here are the Fs. These are shapes of the Fs. So we have a lot of them. So we take the first 4, this one here, this one here, this one here, and this one here are all the same shape, just pointed in different directions. And this one down here and this one down here are also the same shape in 2 different orientations. And finally, you have the snowman with the double hula hoop. Now, F stands for fundamental, and I have no idea how this is referred to as fundamental, but that's what the letter F stands for, fundamental. So how many different directions they go? 1, 2, 3, 4, 5, 6, and 7. Okay, so the S has 1, the P has 3, the D has 4, and the the D has 5, and the F has 7. Okay. Last piece of the puzzle where we start doing the electron configurations. When these orbitals, and let's go back to, say, the p orbital, for example. When we're talking p orbital, I said the electron can reside on that particular plane. Well, another piece of the truth is every single one of those shells of those balloons can hold 2 electrons. It's referred to as the Pauli exclusion principle. If you make it to AP, one of the things that we discuss is that idea that was mentioned earlier on of this quantum numbers. It says that no 2 electrons in an atom can have the same set of 4 quantum numbers. It's like a magic combination for every single electron. And we're going to see that here also, but not using the terms of quantum numbers. The other thing is, and we're going to see when we're doing the filling in the orbitals, the electrons are going to fill from the lowest level possible, and they're going to fill within, say, the p orbital, where we have 3 different shapes. I would put 1 in this orbital, then I'll put 1 in this orbital, and then I'll put 1 in this orbital, but I can fit 2, so I can put the next one in here, so then I have 2. Next one in air could be 2, and finally this one be 2, so it's completely full. So we add 1 to each level within a particular shape orbital before we start doubling up. That's called Hund's rule. Okay, let's do this. Also, this adding according to the energy levels is called the Aufbau principle. So how do the orbitals fill? Well, this is a very, very good representation, a good tool to remember the order. So when filling up the electrons in an atom, the first 2 electrons are going to be in the 1s. The next 2 electrons are going to be in the 2s. Notice the diagonals. It goes from upper right to lower left. The next 6 electrons, 2 in each one of the 3 orientations, 2 in each one of the 3 orientations would be in the 2p. And then after that, the next 2 electrons would be in the 3s, and so on and so forth. Now, here's where it gets interesting. The next 6 electrons would be in the 3p, but instead of the next energy level being filled is the 3d, the next one that gets filled is the 4s. So 4s comes before 3d. So the next 2 electrons go into 4s. And then the 3d. The next 10 electrons, again, D, there are 5 shapes. There are 5 orientations. And those 5 orientations can each hold 2 electrons. So the 10 total electrons, 10 electrons would go into the 3d. Then the next 6, because p's have 6, would go in the 4p. The next 2 would go into the 5s. And it keeps going. Next 10 goes in 4d. The next 6 goes in 5p. The next 2 goes in 6s. The next 14, and remember there's 7 shapes that go with the F. The next 14 all go into the 4f. The next 10 go into the 5d. The next 6 go into the 6p. And the next 2 go into the 7s. And then finally, the next 14 go into the 5f. The next 10 go into the 6d. The next 6 go into the 7p. And you'll notice this down here, it has this void that the arrow is going through. That would be our location for our 8s. There is not an atom on the periodic table that has an electron in its ground state in the 8s orbital. So there's where your next two elements are going to be. Going to be ones that have 119 electrons and then 120 electrons. Okay, so another way to look at this is that this pyramid, I call it, actually reflects very nicely onto the periodic table. So here's our periodic table. Now I want you to notice on the periodic table that the periodic table has 2 columns on the left-hand side, 10 columns across the middle here, 6 columns across the right-hand side, and 14 columns in the very, very bottom. So the electrons are added according to the periodic table. They're going to, if the electrons fall in any of these locations where there's the s block, they're going to be being placed into an s orbital. If they land over here, then they're going to land in the p block. And land in the middle, those 10, d block, and these 14, f block, meaning the shells that are going to be filled are going to be associated with the particular location on the periodic table. So let's do this. So when talking about electron configurations, there's 3 levels to writing these configurations. First level is what's called an orbital notation. The second level is the electron configuration, the full electron configuration. And fancy word for it is a spectroscopic notation. Full electron configuration, telling you the whereabouts of every single electron in the atom, what orbital it's in, and which what orbital every single electron is in. Now, the benefit of the orbital notation, it not only tells you where it is, which orbital, but it also tells you which orientation. It also tells you that fourth piece, which turns out to be the spin, which direction do those electrons spin in. And then the last way is called a kernel method. It's taking that full, complete spectroscopic electron configuration and simplifying it. Okay, so let's do this. So we're going to go ahead and we're going to draw out a bunch of orbital notations. So we're doing for 3 different elements. When we're showing the electrons are going to be represented by an arrow. And I'm going to use blocks more than lines. I'm going to do it both ways initially, but then I'm going to back off of the lines because making this PowerPoint was easier with blocks than it was with lines. So we're going to say each one of the lines or each one of the blocks represents one of those specific orientations of an orbital. So let's do this. Easiest way to do this is to do this. So let's look at the first one, lithium. Lithium, we look in the periodic table, and lithium has the atomic number of 3. That means they have 3 electrons. If we look at our pathway here, let me go back to it real fast, of how they fill, the first place they're going to fill is going to be in the 1s. So what we would do is we would first draw a box or an underline and label it 1s. And only 2 electrons can go in there, so we put them in. But here's the twist. We put them in, the first one in the opposite direction of the second one. Now, the convention is you draw the first one up and the second one down. Really doesn't matter, just making sure that the 2 arrows are in opposite directions, up and down, not side to side, up and down. So of the 3 electrons, the first 2 fit in the 1s. What comes after the 1s? We go back to our thing, and our pyramid, and we see the next one is the 2s. So if we go back to the 2s, we see that the next block would be the 2s orbital, and the third electron would go into that orbital. Now we have representation of every single one of the electrons that are a part of a lithium atom. If you were to do this with underlines, this is what it would look like. You draw little underlines for the 1s and 2s, and you draw the arrows. Now, like I said, for this presentation, it was easier for me to set this up with the boxes and arrows, but if you draw that out just underlines, that's great. If you do it with boxes, that's cool also. Let's make it a little harder. Next element you have there is oxygen. So if I look up oxygen on the periodic table, oxygen has an atomic number of 8. That means it has 8 electrons we have to count for. So let's do this. The first orbital is the 1s. The first 2 electrons, one up, one down, go into 1s. So now we have 6 left over. The next orbital is the 2s. The 2s can hold 2 electrons, so we put one in, another one. Now here's where it gets tricky. The p's. The p's have 3 orientations. The p's have 3 orientations, so we draw 3 boxes next to one another, or 3 underlines. And this is the next trick, is how do you fill those boxes? We will put 1 in each box before we double up. So right now we have the 2 in the 2s, the 2 in the 2 in the 1s, 2 in the 2s, and then 3 in the 2p. That means for a total of, what is that, 7 electrons. We don't have all our electrons represented, so the next thing we're going to do is add 1 more, but then now we get the double up. I'm going to double up by putting 1 in that first box. This is the orbital notation for oxygen. Every single one of these electrons has a different address and direction. Let's think about this right here. This particular arrow that I'm pointing to here, the one is down in the 2p. That particular electron, it is on the second energy level, 2. It's in one of those shapes that looks like a P. It's in the first of the 3 shapes that look like a P, and it's spinning, I'll say, backwards. There's no other electron on this diagram that has those 4 visual representations. If we were to do this with lines, it would look like this. I would go ahead and draw the lines for my 1s, 2s, and 2p. And I'd, again, fill the orbital by adding them double, double, single, 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 then double it up. Okay, one more. Let's do titanium. Titanium has atomic number of 22. So titanium has atomic number 22, has 22 protons, but it also has 22 electrons. So let's put them in the table. So it's 1s first, add the 2 electrons. After 1s is 2s, add the 2 electrons. So we're nowhere near 22 yet. Add the next orbital, which is 2p, and fill the orbitals accordingly, doubling them up. We right now have 10 electrons accounted for. Next, after 2p, let's go back to that pyramid because we haven't done this yet. Let's go back to that pyramid, and we see that after the 2p is 3s. So we're going to go ahead and do the 3s. So next one is 3s. Let's see, we've only used 10, so we got plenty to go. So this gets a full complement. After the 3s is the 3p. We have 12 electrons accounted for, so we have plenty left. So we're going to go 1, 2, 3, 4, 5, 6. So at this point, we have 18 electrons accounted for. We need to keep going. So we go back to the pyramid, and we say, what happens after 3p? After 3p, we have 4s. So the next electron is going to go in 4s. Now, we have accounted for 18 total electrons so far. We have 1, 2, now we're up to number 19 and number 20. We have only 2 more electrons that we can add. So we go back to our pyramid, which I keep going back and forth to. I should have made this closer. And after 4s, what comes next? Wrap back around, it's the 3d. So let's go ahead and put the next ones in the 3d. D has 5 orientations, so D gets 5 blocks. And we take the 2 electrons we have left over. Right now, the purple lines up there so far are there's 20 electrons, 20 arrows. I only have 2 more. They go in the first 2 spots. This would be the orbital notation for titanium. And every single one of those electrons is in a unique location and direction. And that's what makes this concept of these quantum numbers and the uniformity to be so useful. We know where the electrons are. Every single one has a different quote-unquote address. Okay, so that's the first level, being able to write the orbital diagram. The next thing, which is the busiest one, is to write the electron configuration. Again, it's sometimes called the spectroscopic notation. It's very similar to the orbital notation, but it doesn't take into account the spin or the direction, and it doesn't take into account which one of the boxes it's in. So we're really just looking at what's the energy level and what's the shape. So let me show you what that means. Do nitrogen first. So nitrogen has an atomic number of 7. So I always like to at least mentally go back and say, well, let's start here. Let's draw the orbital diagram for nitrogen. 7 electrons, I put first 2 in the 1s. I put the next 2 in the 2s. That's 4 total. I get 3 more. And then the next orbital is the 2p, and I go ahead and put 1, 2, 3 in there, and this is nitrogen. Okay? So if I wanted to write the electron configuration for nitrogen, it would go like this. How many total electrons are in the 1s? How many total electrons are in 1s? There's 2. So we describe that as in the 1s orbital, there are 2. That's superscript. It's superscript. It's not side by side. It's a superscript on the s. That represents how many are in the 1s. How many total electrons are in the 2s? 2. So 2s2. How many total electrons are in the 2p? 3. So the last part of the electron configuration is 2p3. So the electron configuration for nitrogen, the atom with 7 electrons, is 1s2, 2s2, 2p3. Now, ways to check. The numbers, the superscripts, should add up to give you your atomic number. And here it does. 2 plus 2 plus 3 is 7. Let's do a little bit bigger one. Let's do neon. Neon has an atomic number of 10. So I'm going to go ahead and do the orbital notation, filling that up. 1s gets 2, 2s gets 2, 2p, let's see, I got 4 so far, I got 6. Guess what? I could fill this up. And that is my orbital notation for neon. It has all the 1s and all the 2s completely full. So this is a complete full orbital diagram. To write the electron configuration, I just go across and say, in the 1s, how many electrons are there? 2, 1s2. In the 2s, how many electrons are there? 2, it says 2s2. In the 2p, how many total electrons are there? 6, 2p6. So the electron configuration for the element neon is 1s2, 2s2, 2p6. One more. Just keep getting bigger. Let's talk about iron, number 26. Just a little bit bigger, but it's up there. So first, mentally or physically, draw out the orbital diagram. So again, 26 electrons. Let's go. We have the first 2 go in the 1s. The next 2 go in the 2s. The next 6 go in the 2p. So right now we have accounted for 10 total electrons. The next electrons go in the 3s. Doink, doink. Now I'm up to 12. The next electrons go in the 3p. And I have, let's see, I have 12 right now, so I have plenty. I can add 6 more. 1, 2, 3, 4, 5, and 6. I now have accounted for 18 total electrons. We're getting close. After the 3p, there's the 4s. So we have 18 now, number 19, number 20, almost there. And after the 4s comes what? The 3d. So we draw our D, 5 blocks. We have 6 electrons left for 10 possible spaces. 1, 2, 3, 4, 5. That's Hund's rule. 1 in each before doubling up. And then the 6th one goes there. So to write the electron configuration for this, we simply just go across. There's 2 electrons in the 1s. There's 2 electrons in the 2s. There's 6 electrons in the 2p. There's 2 electrons in the 3s. There's 6 electrons in the 3p. There's 2 electrons in the 4s. And there's 6 electrons in the 3d. So the electron configuration, that entire code at the bottom, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, is the electron configuration for iron. It's a simplification of the orbital diagram, only focusing on the energy level and the orbital, and identifying how many total electrons are in that orbital. So let's do the last piece, the shorthand or the kernel method or the abbreviated version. This is one where we're going to look to find a way to simplify dramatically the electron configuration. So what we're going to do is we're going to look at the periodic table and see what the previous noble gas is to the element. So if I go, and give me a second, if I do the iron, which we just did, and let me see the periodic table here. I go to the iron. Well, that's not a great one. Let's try this. Yeah, that one's better. Okay, I go to iron right here, number 26. And the noble gas, or the noble gas, the one's the noble gas column 18 or 8A, that is right before iron. Let's see, let's go backwards. Doink, 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 doink. Wrap around is argon. So argon is the noble gas that was before the iron. That's going to be the core. So let's go back to the iron for a second. There he is. So up to this 3p, the first set would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And I want to go back and have the beginning part of this iron have the configuration that has just this one here. So let's look at that periodic table again. So the noble gas that's prior to iron, go backwards, is number 18. So if I go to that image there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So up to 3p6 is the previous noble gas. So what are we going to do with that? Let's try one. Let's do potassium. Have our potassium. We're going to do our orbital notation again. I've got 19 electrons, so let's go. Got 1s, 2s, 2p. Let's see, that's 10 electrons. 3s, there's 12 electrons. 3p, 12 plus 6 is 18. Okay, so I can add this 1, 2, 3, 4, 5, 6. And then I go ahead and add my 19th, which goes to that 4s, and voila, that's the orbital diagram for the element potassium. If I were to write that electron configuration, it would look like this: 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. Now, I said for this abbreviated or kernel or shorthand method, you take and you have to identify what is the noble gas that precedes this element. On this particular element, if again I go back to that table, for potassium, right here, number 19, the noble gas that was before it was argon with number 18. So I start with putting in square brackets AR, the symbol AR. That symbol AR in square brackets represents that portion of the electron configuration. Just simply writing square bracket AR square bracket says 1s2, 2s2, 2p6, 3s2, 3p6. So it's a replacement. It's a shorthand. So we drop the 1s2, 2s2, 2p6, 3s2, 3p6, and we just write argon in square brackets. And then we put the rest on the electron configuration, 4s1. This is the simplified, the abbreviated, the kernel version of the electron configuration, where it shows you the core electrons, the ones that are prior to the core electrons that precede the last electrons in the element. Okay, let's try another couple. New cobalt. Cobalt's number 27. Let's fill that up. 1s gets 2, 2s gets 2, 2p gets 6, 3s gets 2. Let's see, that's 2, 4, plus 6 is 10, plus 2 more is 12. We're way far away. After 3s comes 3p. 1, 2, 3, 4, 5, 6. Okay, now we're at 18. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. We have 18 total electrons. Let's keep going. After 3p is 4s. Add those. Now we're at 18 plus 2, that's 20. Keep going. After 4s is 3d. We have 7 electrons left. So 1, 2, 3, 4, 5, 6, and 7. This is the orbital diagram for cobalt. Now, let's write the full electron configuration. We start at the beginning. There's 2 electrons in the 1s. There's 2 electrons in the 2s. There's 6 electrons in the 2p. There's 2 electrons in the 3s. There's 6 electrons in the 3p. There's 2 electrons in the 4s. And finally, there are 7 electrons in the 3D. So the total, full, complete electron configuration for cobalt is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. Let's simplify that. So again, in order to simplify it, I need to go back and look at my periodic table. Let's say I got cobalt here. So I have cobalt right here, number 27, and I need to go backwards. So I go backwards, and again, just like the last example, argon is my previous noble gas. So if I want to say do argon, I start with the symbol argon, Ar, in the brackets. That argon again represents that portion of the noble gas, that portion of the electron configuration. So we can drop that part of the electron configuration, just write the letter Ar in a square bracket. And then we finish it up by doing 4s2, 3d7. Last one, let's do iodine. That's kind of big. Iodine has 53 electrons. Let's get them all done. Let's go. 1s, there are 2. 2s, there are 2. 2p, there are 6. And next is 2s. 2s, there are 2. After 3s is 3p, and there's 6. Okay, that's 18. I know that because we've done it a couple times. We got tons. After 3p is 4s, and after 4s is 3d. So let's see what we got here. At this point, we have 30 total electrons accounted for. That's a lot. Let's go back to our pyramid to see what comes up after 3d. So after 3d, let's see, here's 3d. Next is 4p. And then, if we need it, 5s. So let's go back and finish this up. After 3d is 4p. So we say we have 30 here, 31, 32, 33, 34, 35, 36. Cool. After 4p comes what? Do we need to go back there? We already just said it was the 5s. So we add our next 2 there. So it's 36 plus 6. 36 plus 2 is 38. Okay, we're on our way. After the 5s is what? Let's go. After the 5s is the 4d. So go to 4. Oops, I won't do that. After the 4d, 5s is the 4d. 4d has 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whew. Let's see, we had 36, 38, plus 10, 48. Oh, we're almost there. What comes after 4d? Do we need the pyramid? After 4d is 5p. So we go back and we finish this up, and the next electrons fall in the 5p. And we go across, we have 1, 2, 3, 4, and 5 electrons in the 5p. So we now have accounted for all 53 electrons. So we had 48 up to here, 49, 30, 50, 51, 52, and 53. We have all of them accounted for. The electron configuration for iodine would be quite lengthy, which is one of the reasons why we had the kernel method. We'd have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and finally 5p5. So let's simplify that. Let's look at the periodic table. So we're doing iodine. Here's iodine right here. We go backwards. The previous noble gas is krypton. Krypton had 36 electrons. So let's find it. 36 electrons. 2, 18, 20, 36. This one here. The 4p being filled is krypton. So if I were to draw this one out, I would start with krypton. And krypton is all the way out to the 4p. And then I just tack on the remaining parts. 5s2, 4d10. Ooh, should have been 10 there. And then 5p5. Technical error here. That should be a 10 right there. So you can see that the kernel method, the abbreviated method, is much easier, but it still has a lot to do where you have to think about it in the orbital notation method to get there. I want you to also notice, if we go back to this periodic table, that all these noble gases are in the p block. So all the noble gases will end in p6. It has the 6th electron in the p orbital. Okay, let me finally connect this to bonding and valence electrons. So the outermost principal energy level in the atom are the ones that are going to be involved in bonding. Those are the valence electrons in the valence shell. The electrons in the valence shell are called valence electrons, and these are the ones that have the highest principal quantum number. So let me go back to what I didn't want to go back to the last one. Go back to iodine. So let's look at iodine's electron configuration. And you can even look at the kernel method. How many electrons, we'll look at the kernel method, abbreviated first, have the highest number out front? So we have 5s2, 4d10, sorry, 10 should be there, 5p5. So in the notation for this atom, the 5 is the highest number out front. So how many total electrons are in all the 5s? It's 2 plus 5, or a total of 7. Now, here's what is really cool about this, I think. If I go back to the image here, and I notice where iodine is, it's right here, number 53. It is in the 1, 2, 3, 4, 5th spot in the p block. But remember when we're talking about the valence electrons, and we said the number in front of the A represents the number of valence electrons? Here's 53. It's in column 7A. It only counts the 5s and the 5p. So it has a total of 7 electrons in the valence shell. Kind of cool. So if you can just identify the number of electrons in that outermost shell, you can do it with the periodic table like this one, where you can look at the letter A across the top, or have the complete electron configuration. Now, last thing to talk about is ions, which I didn't make the rest of this PowerPoint for, so maybe I will actually do that as an addendum in a few minutes. Last piece of this lesson is about electron configurations for ions. So I'm going to remind you that there's 2 types of ions. There are anions, which are negatively charged, and there's cations that are positively charged. In order for something to become an anion, it has to add electrons. In order for something to become a cation, we have to remove an electron. And here's where it gets tricky, weird, is you have to pull the valence electrons first. I'll show you a couple examples, but the valence electrons go first. So let's do this. If we had sulfur with its 16 electrons, 1s, 2, 2s2, 2p6, and 3s, 2, that's 12. And then 3p's next, 12, 13, 14, 15, and 16. That's sulfur. So it has the electron configuration of 1s2, 2s2, 2p6, 3s2, and 3p4. Now, what if we had the sulfide ion? The sulfide ion is the sulfur with a -2 charge. So what that means is we have to add 2 electrons to the sulfur. So we have our sulfur, and the sulfur looked like this, right? We have to add 2 more electrons, 1, 2. So the electron configuration for sulfide, would be 1s2, 2s2, 2p6, 3s2, 3p6, 4. Oops, that's it. Now, let's look at cations. Let's go back to iron. This was our electron configuration for iron. I literally just moved this slide from earlier. Now, what if we looked at an iron cation, maybe the iron +2 cation? Now, what does it mean this +2? The fact is +2 means it has to lose 2 electrons. Lose 2. So that means we have to have a total of 24 electrons. Here's the trick. The 2 first electrons that are to be removed from the iron are the ones with the highest principal quantum number, or the ones that have the largest number out front. And that would be this 4. 4 is the biggest number. So the first 2 electrons that get pulled for this are that one and that one. So now I got rid of this 2. So there's now no longer going to be a 4s. So we get rid of the 4s, we move over the 3d, and this is the electron configuration for iron +2. 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6. One more. Let's look at nickel. Nickel has 28 total electrons. Nickel's orbital diagram looks like this. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 6. What happened? Okay. Okay, so I'm going to just fix this. So there should be one more electron here and one more electron here, which will show up nicely on the next slide. So electron configuration for nickel would be 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, and then 3d8. So what if we had to do a ion? So nickel, well, there they are. There's my 2 electrons. Nickel has 2 different versions, +2 and +3. So we're going to do +3. So we're going to start with nickel. And then once we have nickel, we need to do a +3, which means I'm going to lose 3 electrons. Nickel has 28 electrons, minus 3, you got 25. So I need to remove 3 electrons. The first 2 electrons that are going to be removed are from the highest principal quantum number, and that's 1 and 2. 4s goes away. I need to lose 1 more. Of the remaining filled or partially filled orbitals, the 3s are the next highest principal quantum number, or ones with the highest shell level. So the third one comes out of the 3d. So I got the 3d, that one, that third one comes out of there, leaving us with a new electron configuration for nickel +3 that has the 4s removed and the 3d dropped down to 7. So that's the electron configurations for ions. Hopefully that helped. I know this is an incredibly long video, but it's a pretty complicated topic, and it has a lot of explanations to go on. I will see you in class.